Let's take a look at the fundamental theorem of line integrals. A quick example. And what I want to do is I want to find a function f such that this vector field is actually equal to the gradient of this function f. And I want to use it to evaluate the vector field that's given by y squared over 1 plus x squared I plus 2y arctan x j. And it's along specifically this path t squared plus 2t, t goes from 0 to 1. Now, looking at this right away, I know that what I need is I need f, this guy, to actually be the gradient of some function f. So I can say right away that I know the partial with respect to f, if this is true, the partial of f, with respect to x, is going to be equal to the x component right here, which is y squared over 1 plus x squared. Well, that tells me then that this function f must be equal to the integral of y squared over 1 plus x squared dx. So when I take the integral, what I get is y squared arctan of x plus g of y. Now, the reason I have this g of y here is this is my constant. This is my constant of integration. This was an indefinite integral. So you know I have plus c is the way we typically write it in single variable calculus. But this could be a function of y, or it could be truly a constant. If it's a function of y, then it is a constant with respect to x. So I just need to figure out what this thing is going to be. So I now know that f of xy has to look like y squared arctan of x plus some function of y, which is my constant of integration. So let's just take the partial out with respect to y. The partial of this with respect to y is going to be 2y arctan of x plus, this is some function of y, I don't know what it is, so it's just g prime of y. Now when I compare this to the y component, I see that this is exactly what I have here. That would then imply that g prime of y is 0, which then tells me that g of y must be equal to some constant k, because that's the only way I'm going to get 0 when I take the derivative with respect to y. It cannot be a function of y. And likewise, it can't be a function of x, else it would have showed up back over here. So because it can be some constant, I'm just going to take k to be 0. Now, keep in mind that when we do this, we're going to find f, this guy right here, accurate to within a constant. And that's it right there. So this is going to be accurate to within that constant. Because I'm really interested in the gradient of f, whenever I take the derivative of this constant is always going to be 0, so I will have the correct gradient. So again, this function f will be accurate to within a constant. So now I have f. I know f of xy is going to be y squared arctan of x. And sure enough, the gradient of f equals the partial with respect to x, which is going to be y squared 1 plus x squared I, plus the partial with respect to y, which is 2y arctan x j. And this is exactly my vector field. So now that I found that, I can use the fundamental theorem of linear or of line integrals, and I can simply integrate over this curve by only being concerned with the starting and ending points. Now notice the starting point is when t equals 0. When t equals 0, we have this initial point is going to be r of 0, which equals, 0, 0. And for t equals 1, we have r of 1, which equals 1, 2. Now notice I wrote these both as position vectors. So now I can go ahead and go directly to the integral. I can say that the integral, the line integral, of the gradient of f dot dr, supposed to be a vector there, is equal to f of 1, 2 minus f of 0, 0. There's these coordinates that I'm taking off right there, which is equal to y squared tangent of x evaluated from the points 0, 0 up to 1, 2, which is going to be, let's see, at 1, 2, x is 1, y is 2. That's going to give me 4 times, whoops, I wrote tangent. This is supposed to be arctan. There we go. This is arctan. So I need arctan of 1. Well, arctan is 1 when sine equals cosine between 0 and pi over 2, which means pi over 4. So this is 4 times pi over 4 minus 0, 0. That's just minus 0. So my solution is actually simply pi.